feel like the whole thing is like, you know, that's your fun. This is. On the surface, so is the height, is the evaporation, so that it goes then, it's the gray thing. It is both, and then in the middle like that. Like if you look at the. It is, but then it goes down and then it goes up. Okay. It's like, it doesn't make sense. Driven chemistry. Mr. Anderson, what page are you?
I'm just gonna pick out problems from,
The back.
yeah. I'll just create some problems too.
Do you have any paper?
It's at the top. Um, it's on the shelf, top shelf. All right. Okay. Let's start off with the PVA problem. So if you guys want to just copy this down here. Okay, so given the acceleration function, and given that velocity of 0 is 1 and x of 0 equals 3, find the position function. Okay, so just to establish some relationships here, if I'm starting with acceleration, we know that position's derivative is velocity, velocity derivative is acceleration. So if I'm starting from the acceleration level, I can move up the chain to velocity and to position by taking the antiderivative. So if I want to find velocity, I could take the antiderivative of acceleration. That'll lead me up to velocity. Okay. And then likewise, oh, and then I could take the order pair, plug in at the velocity level and solve for C. And I can repeat the process again from velocity to position. Position is the antiderivative of velocity. And that'll bring me up to, wait, hold on. I got this. Let me try that again. So yeah, what I did was not wrong. It was just easier to write this way. So if I take the antiderivative of acceleration, that'll bring me up to v of t plus c. And if I take the antiderivative of velocity, that will turn into position plus c. Okay, so we're starting at the acceleration level. I can take the antiderivative of acceleration. That will, step by step, lead me up to velocity. Okay. So antiderivative of acceleration 3t minus t to the negative 1/2. I'm just getting both terms set up nice and ready for power rule. Okay, so once I got that t to be t to the 1/2 and brought it to the numerator, it became t to the negative 1/2. Now I'm ready to do power rule. 3t becomes 3t squared over 2. T to the negative 1/2 becomes t to the 1/2 over 1/2. And then plus c. We're gonna do some cleanup. Push the fractional 2 out in front, pull the 1/2 up to the top. And now I'm at this is the general equation level. But how can I solve for c at this level? So do I have an order pair that I can use to solve for c? Well, 0, 1. Yeah, so 0 goes in for t, 1 goes in for v of t. V of t kind of like our y value. And then we can solve for c. Okay, so 0 in for t, 1 for v of t. The 0 is nice. It wipes out all those terms. We solve for c. C equals 1. Now we can update our velocity function. So we're halfway there. With acceleration, we moved up to velocity level. Now, one more process to bring us up to position, right? Any questions so far? Okay, so now we can take the antiderivative of velocity. Looks like every term is already nice and ready for power rule. Three halves t cubed over 3. Okay, 2t to 3 halves over 3 halves. 1 becomes 1t. And then plus c sub 2. Okay, so now I'm sitting at the general equation level. Plug in the order pair. Order pair that's available to me is 0, 3. So 0 in for x, 3 in for x of t. The nice thing about 0 is it wipes everything, wipes a lot of stuff out. So this is like kind of like our y value, our t is like our x value. So c equals 3, and then now I can update my position function from general to specific. Yes. Yeah, I don't have to put it in radical form. Either form is fine. Let me see. Okay, I have a depth integrals with trig that I want you to try here. Okay, so first things first, we ignore the bounds, right? The bounds is not going to involve with our expression just yet. So if it helps, I want to rewrite it without the bounds, forcing you to focus on this problem. So we know we don't have a single rule that can handle this, right? We have 6 trig integrals, but none of them look exactly like this. So we got to think about use substitution. So let's get a set of parentheses to show up. So what could be our u value that will work with this problem? Sin x, okay. Derivative of sine is cosine, so we know that's going to work out nicely. Okay, make my substitutions. Okay, do the x's go away nicely for us? They do. Numerator, denominator, cosine goes away, no leading coefficient. Nice clean power rule for us to apply, much cleaner than what we started with. So u cubed over 3. Now we can think about the bounds. Okay, because there's not going to be a plus c. But can I use the u cubed over 3 with these bounds that I see here? Not yet. Okay, so there's 2 options. Either the bounds in terms of u, and I can apply that with this antiderivative, or I bring this back in terms of x, and then that way I can use these bounds. But I can't use the x bounds with the u variables. Okay, so I'll go through both methods. And you guys can choose on the test. You guys don't have to do one versus the other. You can just choose, but just make sure you don't use these with the u. Okay, so if I want to bring the u back in terms of x, u is sine x, so sine x cubed over 3. Okay, now I can use these bounds. So pi over 6 and negative pi over 3. Okay, upper bound first. Okay, so once you put this in, you cannot leave your answer like this. You got to go one step further. You have to evaluate these trig. Now, these were numeric values. You could leave it like this, but on the AP exam, on the test as well, we have to finish evaluating our trig value. So sine of pi over 6 is 1/2. Sine of negative pi over 3. If you think about that in terms of it's in the fourth quadrant, same thing as 5 pi over 3. If I add 2 pi to it, so sine in the fourth quadrant is going to be negative. Okay. I'll continue cleaning up, but this is more acceptable than this. At least here you've gotten everything down in terms of as a numeric value. We keep going, we can pull the 1/3 out, make that 1/2 cubed 1/8. So any of these variations are fine. Oops, sorry. The minus a negative becomes a positive. Mm-hmm. No blanking a circle. Yeah, on the AP exam, they don't provide that, so I'm gonna mirror that on the, yeah. I see. Okay. Any questions, guys? Oh, that's right, second method. I haven't forgot about that. So the other method is where we're able to hold on to this u cubed over 3, but then we adapt these bounds to be in terms of u. Okay, so here's method 2. Okay, so my initial u value lower bound is if x is equal to negative pi over 3, then the u is equal to sine of x, right? Because that's the assigned relationship between u and x. So I plug negative pi over 3. Fourth quadrant, so negative root 3 over 2. Okay, so that's my new lower bound. If x is equal to pi over 6, which is 1/2. Okay, so we have our new lower bound, new upper bound in terms of u. So now these compare nicely with this u cubed over 3. New upper bound, pi over 6 becomes 1/2. New lower bound, negative pi over 3 becomes negative root 3 over 2. So insert 1/2 in for u. Same result. Just different order of processing information. Good to know both methods so you know where these are coming from. But if it's free response, like on this test, you can choose whichever way you want to do it. Okay. Let's try a second theorem problem. So here's the rule here. The rule says if I have the derivative of a definite integral, so we can only do this if a derivative and integral are attached to each other. Okay. Now I said before that we never plug the bounds directly into the function. This is the exception, right? Because we're not doing the full integral, it's derivative of the integral. So that allows us to just insert directly in. But normally if it's an integral problem, we got to deal with that issue, right? But here, these two operations have a way of undoing it. So if both the upper and lower bounds are both variables, we take turns with them and plug in the upper bound, but we also have to involve the derivative in that process as well. So it's f of p of x times p prime. Now, if q of x is a constant, then that's it. There's nothing more that we need to do. But if the lower bound is a variable, then we have to repeat the process for the lower bound and do the same thing here. We say f of q of x times q prime. So f of p of x and f of q of x, all that means is I'm replacing the variable in the expression with the upper bounds expression. Here's an example. So derivative and integral are paired next to each other. That allows us to go directly into evaluating that upper bound. So root x inserts itself in for the t. Multiply this by p prime. P prime is the derivative of the upper bound. X to the root x is the same thing as x to the what? 1/2. Go through that power rule there. So that's my p prime. Okay. Any questions there? Right. Minus. We got to keep going because if this was a constant, we will leave it alone. There's nothing more that needs to be done, but a variable forces us to keep track of it. So 3x squared in for the t. Times 6x. Big parentheses there. All right, do some cleanup. So this cleaned up would be 9x to the 4th, 9x to the 4th times 6x. Let me do a variation of this problem, see if you can do this one here. Okay, what do you notice about this one here? Yeah, variable's lower bound. Is there any way that we can make it turn into the upper bound being the variable and the lower bound being the constant? Flip it, pull a negative outside. Exactly. That way it feels more familiar. Okay. Now we can just worry about the upper bound, f of p of x times p prime, and not worry about the lower bound. Lower bound is a constant. So it looks very similar to what I had to begin with. It's just the signs are different because I had to flip the bounds and change the sign. Okay. All right, let's try this one here. Okay, number 4, x squared times the square root of 6 minus x. Yeah, it's at the top of the shelf there. You can grab some paper. Okay, so anytime we see a expression that only involves variables and no trig, we always want to explore option number 1, right? Can we do this with just the expansion power rule? What do you guys think? Can I distribute my way through this? No, that square root with multiple terms inside, the order of operations forces us to not able to be moved, to move that. Now, if it was just parentheses 6 minus x squared, then I can FOIL out, but here I can't FOIL out, I can't distribute, I'm stuck. Okay, so at least we know, okay, I can't expand this, I got to rely on U substitution. So now we can explore our second option. Okay, parentheses 6 minus x to the okay, what's our U value? 6 minus x, right? Parentheses. All right, is this going to be one of those problems that the x goes away nicely for us? Yeah, no. Okay, so we know this is going to be, we're still going down the right path. We just have an additional step. We got to worry about that x squared is not going to go away on its own. Okay, so our U value is 6 minus x. Okay, we make our substitutions. Okay, what's the issue here? Yeah, the x's don't cancel out. We can't move forward until that x is resolved. Is there a way to replace that x in terms of something else? Yes. Say it again. That's right. Du over -1
But I can force a -1 to the top without changing. Right, so that's nice. Yeah, back in. Yep, solve for x. So x equals 6 minus u. So this piece is going to go in for this x here. Yeah, I see some students do this on the test where they get to this point and they try power rule anyway, and they do x cubed over 3 times u to the 3 halves over 3 halves plus c. Okay, we can't do that. Okay, this feels like an easier path, but it's not. It's not the correct way. Okay, we have to spend the time to deal with that x. All right, so now the x gets replaced with 6 minus u. Okay, so now we're still not ready for power rule, but at least we have a path towards it, right? If I take the time to FOIL this out, I can move these things, these terms in the front. If I FOIL, I can distribute that negative u to the 1/2 through, and then power rule is available for us. So 6 minus u times 6 minus u is 36 minus 12u plus u squared. We're almost there. We're still holding on to all these integral notations because we haven't gotten to the point where we can do power rule just yet, but then after the next step, we'll be able to. Add exponents, 1/2 plus 1 is 3 halves, 1/2 plus 2 is 5 halves. Right, so now we can jump into power rule. Every term is nicely ready for us. All the x's have been taken care of, all the parentheses have been taken care of. Okay, 36 divided by 3 is 12. 12 times 2 is 24. Now make sure I bring all the u's, replace all the u's with x's. Okay, any questions? Okay. All right, so I encourage you guys to continue looking over the list of problems that you're going to see on the test. So power rule of integrals, use substitution, change a variable, we did that. Trig integrals, depth integrals involving trig, we did that as well. absolute value function, just have to understand you have to draw your graph. Think of it as two triangles and add up those two triangles. We'll do that in the class as well today. Even in odd functions, we'll practice some more of that today in class. Second theorem, we did that today. Average value theorem is basically height equals area divided by the width. So the formula looks like this: 1 over b minus a, integral from a to b of f of x dx. Okay. We go through whatever process we need to take care of, evaluate the upper and lower bound, and then multiply by the 1 over the width. And then we did this at the beginning of our help session. Second derivative, antiderivative gets up to first derivative, and then first derivative, antiderivative brings up to position. Or a of t integral becomes b of t, integral of that becomes x of t. All right, let me know if you have any individual questions.